Okay, my name is Dawid Weiss, or David Weiss, like we established during the evening 2 days ago. So whichever you want, I'll probably respond to. And this talk, unlike most of the other talks during this conference, this talk is not about Solr and Lucene directly, but about things that came out from Solr and Lucene that I think are worth knowing and I think may be applicable to other projects that you have and I think you can all benefit from. So maybe I'll start with a little bit about myself, a little introduction. I really like coding. Like, if you know me, you'll know that I like coding a lot. Like, this presentation is actually coded in LaTeX. Not many people do this nowadays. I really like coding. And I've coded for a long time in assembly, and that's why pointers and data structures, simple data structures, like the one that was presented in the keynote speech this morning, I like them too. I mean, the object-oriented programming is an unnecessary layer of complexity over pointers. That's what I think. So, I may not be the right person to talk to if you like object-oriented programming, but I live with that. I also used to be a researcher. I used to be a university professor. I'm not anymore, but I hold my PhD proudly, and I can show it to you anytime you want. But within this community, my PhD is actually pretty lame because everybody here is a practitioner information retrieval specialist, so it really doesn't, there's nothing to show off with. I do like open source, and I contribute to many projects. We also have a company, so I'm part in business as well. So I'm kind of everywhere. I have an attention deficit disorder. I'm like, everywhere. So what we're going to talk about today is tests, basically, software tests. And I'm pretty surprised there's so many people interested in software testing because usually it's a thing that, not many people like knowing about, not to mention doing. So I'm really happy to see you all. We'll talk about randomized testing, why it's good for you. We'll talk about how to put assertions in code and tests that you don't know what the input will be for. So how to assert on something that is pretty much pseudo-random or random. And I will try to introduce the frameworks, the tools that can be handy, but are not necessary, are not crucial for implementing these ideas. So consider this talk an introduction to an idea, not necessarily an introduction to a tool. Now, unit testing, like we've been told, everybody will tell you tests are good. The more tests you have, probably, most likely, the better software you have, the fewer bugs you have. Now, all tests should theoretically cover boundary conditions that your test, your code, your production code has or may hit in the future. And unfortunately, there are a few assumptions that are just wrong about that. I mean, the first assumption is tests, static tests, once they are written, no matter how many times you execute them, it's still the same code. It's still the same execution path. You can run it 1,000,000 times, and it's just as good as if you just ran it once. And obviously, if you're changing your software, it may detect regressions. It may detect changes that your software changed in a way that is not compatible with the test that was written for a previous version. But it doesn't yield any new value for you. With each run, it doesn't bring you any new information about how good your software really is. Plus, there are complex interactions within software that are just not even hard to implement. They're impossible to explore and to anticipate. And I'll show you some of these today. Within the trend of being environmentally friendly, I would like to say that if you run a lot of static tests, you're just contributing to the global CO2 pollution. So you're a bad person in general. I mean, really, you shouldn't be. OK, so let's just first try to motivate why random testing is good. If you take a look at this example, and I hope people in the back can see it, this method picks from a random number generator. It picks a number, takes an absolute value of it, gives a modulo of the, wait, this is not politically correct. Oh, no, this is better. Okay. So it takes a random word off the list and just prints it, 100 times, right? Now, can this ever fail? Ever? Apart from somebody coming and sticking a knife within your circuits or something. Well, most of the people will say no. I mean, no, it cannot fail. So we run a test for it, and this is a randomized test. It actually starts with the random. Every time you run it, it starts with a different random. And once in a while, it may take a longer while, but once in a while, you'll hit an exception. And this is an exception that is pretty much weird, because you hit an array out of bounds exception with a -3 pointer. How can that be? Well, does anybody know? Java 7. This is the new optimization introduced in Java 7. It's called the -3. Now, the one book I can recommend if you want to, find out how little you know about a language, go and buy the Java puzzlers. And it's really, even for advanced, software engineering, this book, you'll be like a 25% correct answers if you're good. Well, before I tell you why it's so, I need to motivate why randomized testing and why that test wasn't particularly good. Well, that was a randomized test. The question is, once you hit something like this, how do you repeat it? How do you tell, OK, I've hit some boundary condition. Now I want to do it again so that I can debug it. So I can put logs in and stuff like that. How do you repeat it? How do you debug it? There's just no way, because you don't know where you started from. So randomized testing, in the essence, is, OK, go randomly, but somehow remember the seed you started off with. OK? And that's pretty much it. That could be the end of my presentation, but I do have some more treats for you. So in this case, here, the screenshot here, the seeds, the starting seeds for each test case are both in the name of the test case here, and this is a standard JUnit runner within Eclipse. So they're both encoded here, and there is another treat because they're encoded in the Stacktrace, and I'll show you how it's done later on. And now, once you know this information, once you know that your test crashes on that seed, you can actually try to repeat that test again and again. And in this case, I just copied the seed from here. I copied it on a method, and I can rerun it. And this method crashes every time. And it crashes because there is no binary complement to integer dot min value. So there is no positive value for that particular integer. And that's why math apps doesn't always return a positive number. OK, boundary conditions are everywhere. I mean, this code is still in Lucene. It's in test cases in Lucene. Can this ever crash? And a better question is, how can this crash? Is it going to just return the wrong number outside of this range? Is it going to crash with something unexpected? The answer is, if you run it like this, it's going to crash with an illegal argument exception. So it's going to actually throw an exception on you. Boundary conditions are everywhere, and there's just no way to predict them. I mean, you can react once you hit them, but there's just no way to, with the complex software, predict all the different use cases. Now, Michael Bush was showing this morning a cool piece of code that I just couldn't resist not to insert here, because it shows how little control we have over the software that we write. I'm sorry. And I wrote, can you see this? OK. I wrote a demo that is pretty much what he did, but without the volatile, without the memory barrier. So what happens is that you start a thread, that thread on top of there, it sleeps for 1 second, then sets a global variable ready to true, and the bottom thread just spins and waits for that variable to become true, after which it says, done, I left the loop. Simple. Now, if you run this code, oh man, okay. Okay. Now, if you run this code on Windows, it'll happily complete and say, done, I left the loop. Now, if you run this code on Unix, it just hangs. Now, you may be blaming Linux because it's it's an open source system. But then, here's this example on macOS. Can you see this? Is the font all right in the back? Okay, I have 2 shell windows, and this one is the same machine. I didn't SSH to somewhere else. These are 2 shell windows, the same folder. I'm not cheating, okay? I'm running this one, and it hangs. I'm running this one, and it completes. Now, in the face of this, what does a developer do? Find the 10 differences. I mean, damn it. Now, what the developer usually does is probably this. That's what I usually do this. What happens is it's a different VM. I'm sorry. Okay. So one of them is a server VM. This one is a server VM. And this one is a client VM. And it's actually the detection between the server and the client. It can happen at runtime, so you may not have the control on which one is picked. And why does it hang or why it doesn't hang depends on the compiler that the VM chooses, whether it's C1 or C2. If you want to know more about this, buy me a beer and I'll tell you. So now back to the real thing, randomized testing. As a historical note, I don't think this is a totally new idea, and many people have confirmed that this has been applied in projects in the past. But I learned about it in Lucene for the first time. There are a lot of great, interesting ideas within the Lucene test framework that we utilized within Carrot Search to our code, and we're happy with. So I can't really attribute this to anybody, in particular, which I'm really sad I can't. But if you know who came up with this first, then tell me. Now, the randomized testing manifesto is each execution of a test covers a different execution path. So each test is different, starting from a different seed. Within the same seed, they are repeatable. So if you do start from the same seed, the test should execute identically to what it was before. And this is actually quite hard to achieve, but sometimes, yeah. Well, I'll be talking about that. But this is how it should be. Now, the third is the test should be executed a lot of times. The more you run your test, the more of the execution space you'll explore, and the more you'll know about your software. So a build server, or the willingness to participate in such an endeavor of developers, which is hard if your tests run for 4 hours, is actually crucial. How can we randomize tests? What can we do to actually make them run randomly? Well, and I'll be using raw examples from Lucene code here. What you can do is you can randomize input data for your algorithm or program. You can randomize iteration counts. You can randomize arguments. What does it mean, randomize? Well, you can go completely random if your algorithm allows that, or you can shuffle the order of something that is valid for your algorithm. Or you can, pick something from a constraint-based space, like, I don't know, a range of values or a range of different symbols. And here, this snippet of code here shows an example where, randomly we pick either a realistic Unicode string, which is just, it selects randomly a Unicode plane to choose from and then picks characters from that point, or just go with the random string. The more randomization you give, the better. Now, you can also randomize software components. And if you know Lucene, there are many implementations of the same contract, be it an abstract class or an interface. You can pick different implementations. Uwe was talking about it, like index writer, analyzer, I don't know, whatever, codec. And if the contract says they should be interchangeable, well, it shouldn't play any difference which one you pick. So here, again, a snippet of code picking a different implementation of a directory as a string, and then it's converted to a directory. This is, it goes in levels. A more generic level is changing the environment. What I've shown you with that hanging or not hanging example is a perfect use case for demonstrating how a single program, the same program, can hang on one environment and run on the other. And switching, running your tests in different environments, in Windows, in Mac, in different flavors of Unix or Linux, it catches lots of subtle bugs that nobody came up with before or didn't think of, like the locale or time zone or operating software quirks. And finally, the last thing you can do is try to cause artificial exceptional triggers, like simulate slow disk or simulate a bad sector on a disk, so a failure, an I/O failure, or a socket failure. All these, pretty much go down with increasing complexity of how to do this. But if you want examples of how it's been done, the Lucene test framework provides these. OK, so how do we assert on whatever it is that is random? Well, we can do it, again, in a few ways. The first thing is we can know the exact output for whatever random input there was because we have more than one implementation. And this is actually pretty common. Like you write an algorithm in the simplest possible way, then optimize it. If you optimize it, it shouldn't differ from the first version implemented. So use that as a reference and compare the two outputs. There are libraries, different libraries that you can compare against that implement the same algorithms. Again, compare against something that is known to work. Sanity checks. If you have a code that has contracts like, absolute number, does it always return a value that is greater or equal to 0? You can put checks or assertions on those boundaries, on those sanity checks. It doesn't care about exact value, but it does care about the contract of what a method or a program should return. And finally, it's actually a very good way of testing not to expect anything from a random test other than not expecting a crash or a JVM core dump. And I'm sorry to say, but the JVM core dumps are frequent within Lucene, for instance. They are more frequent than you'd like them to be. I mean, that doesn't really encourage people to write in Java if you have a core dump from the Java virtual machine at some point. That is not, possible to explain in any reasonable way. So even not checking anything is actually a good way of testing. Now we get down to tools. And like I said, the idea is pretty simple. So you can use any homegrown solution that you can come up with. I mean, just, pick a random seed from the current time, log it somehow, even by just printing the system out, and then pass it to your tests. And the thing is, it will work. I mean, it works just fine. If you do want some infrastructure, Lucene does provide the framework or a JUnit runner and a base class for extending your own tests that takes care of many little, subtle thingies that you may want to re-implement yourself, like picking numbers or shuffling things or shuffling tests. But that piece of code is actually pretty closely connected to Lucene. So it does many things that Lucene expects. And what I wanted at some point is to extract just a minimal subset of code that would be portable in between projects, like between projects, that wouldn't rely on Lucene being on class path, that it could be used separately. And on a way of implementing that, perhaps make the code a little bit less hairy. So to make a randomized test, basically you extend some superclass within these, and you can use the infrastructure they provide. So from now on, I'll be talking about the randomized runner because I implemented it and I'm vain. What does it do? The process is as follows. We start from a master seed, okay? Master seed value. And this master seed value can be passed to the runner using a global property, using annotation on a class, or just it's picked, if none of these is available, it's picked randomly from the current time, hashed by murmur hash, so it's pretty random, actually. Then there's the suit validation. Is everything OK with the class? Is everything accessible, et cetera, et cetera? It's pretty much as in JUnit, only a little bit relaxed. So for instance, you can have your static hooks, class hooks. You can have them private, not only public. And this is something that we think it should be like in JUnit, but it's not. So it's an arbitrary decision. Then based on that master seed, every single test case within your suit, within your class, every single test case gets assigned the method seed. So there are two seeds, the master and the method seed. And they are derived from each other. They can be overridden individually, but if not, if you don't do anything, they will be derived one from the other. Finally, there's the shuffling of test methods to ensure that test methods don't depend on each other, which they shouldn't. Yeah, it's not a bug. I mean, Java 7, the reflection in Java 7 doesn't return methods in the order of their declaration in the code. And to some people's surprise, that was never a contract. So the fact that it did return them in the declaration order was just a coincidence, So better be sure. I mean, shuffle them, and you're sure that they don't depend on each other. So the shuffling, just to show you how it works, these are two classes, class 1, class 2, that is a subclass of test 1. And they have hooks, class hooks and method hooks, and they print the current life cycle that they're at. Basically what shuffling is about is, if you run them 3 times, you want the class hooks to be around all the test cases in order of superclass to your suit class. You want the method hooks within the instance to be in the same order, again, around test cases. But every single of these test cases, every single run is different. Every single run you run them, it'll be in the different order. Okay? So if they actually do depend on each other, it will come out at some point. There's just no way. And if you do use the randomized runner, for instance, in Eclipse, every single test method will have an appended seed that you can just look at, write down if a test doesn't pass, or copy to your code and make a test case that is fixed with that seed. So these are 3 runs, and you can tell that the master seed on all these 3 runs, it's different, and the method seed, again, on all these 3 runs, it's different. Now, there's a lot of infrastructure within randomized runner, but basically, there's something called a context. And this context object here, it's a thread local. So within a thread, you see the randomness that you've been assigned with, and nothing interferes with that. And this is an attempt to make tests predictable, especially multi-core, asynchronous, multi-thread tests, which are really hard to ensure they will run repeatedly in the same way. But this is an attempt to do that. So the context is thread local. Every single thread spawned from a test will get assigned the same seed, if they started from the same seed. Then you can get the random, but you can't set the seed. It's a subclass that will forbid you to set the seed. You can check if a test is running nightly, and you can, for instance, if you want to, you can run longer tests on night runs and stuff like that. Lots of scaffolding as well. Again, if you want a random temp fly, random something, shuffling, all these methods are for your convenience. They are static. If you take a closer peek, they are static, but that doesn't mean they share any state with other threads because they reach out for that context that is thread local. So even though they are static, they're actually independent of any other running threads, which is, I think, quite nice. Finally, annotations. There are a few annotations to help you with tests. For instance, you can repeat a test with the same seed or with a different seed a number of times. And this is just a little bit to show you how it works. OK, this test is a nightly test. It doesn't do anything. And this one here, this one here below is a test that fails 50% of the time because it depends on random Boolean. So if you run it in Eclipse, for instance, you'll see that all the nightly tests have been ignored because we didn't request the nightly tests to be executed this time. Now, that test always method, it was requested for it to be executed 5 times. Every time it starts with a different seed, and this time it failed 2 times. Now, again, if you take a look, the seed of the failing method here, the seed of the failing method is again injected into the exception that the test case will propagate up the stack to JUnit. This is my personal opinion that, you can lose your system outs and system errors, but an exception you'll finally see, An exception is something that almost always gets to the eyes of the person that runs the test. So if you can actually inject that seed into that exception, that person will be able to repeat that test. How did I do that? I'll tell you later, man. These hands, they do magic. If you want to repeat a failing test, okay, and you may want to do that just to see if a test is failing constantly for a given seed, or if it's not directly related to the seed. And if your tests ran with the same seed doesn't fail some of the time, you have a test case that is not pseudorandom, but random. And that's a bad sign, okay? So here I go. I use seeds that are pseudorandom within my head, so like some hex values can actually be read, like this one here. This is my personal favorite, like Coffee Babe is the Java magic header and stuff like that. This is my favorite hexadecimal number integer. Now, I wrote that and I thought, damn it, not good. Spain, right? Dead beef, not good. But then, not all attempts are successful. Going back to the test, so if you put that annotation on your test and you fix the seed, you can do it either from annotation level or globally and request just that method to be executed. Your tests will run with the same seed. And if you see a consistent failure pattern, that's good because you'll be able to debug it. If you don't, that's good. You know that you need to fix your tests. That's how it works. Now we get to the more complex part of this infrastructure, how to deal with threads. If you do have a test case that spawns multiple threads and then somehow tries to verify the state at some point. Well, what I did, in contrary to what Lucene does currently, what I did was I used a thread group. So all the tests are spawned within a single thread group, and subthreads inherit the thread group of their master. So at any given point, you can actually check how many threads have been spawned, assign their seeds, and do all that magic. And it helps a great lot to ensure they are at least partially predictable. But if they do have, in between threads, if there are race conditions, obviously that is not going to fix anything. So if you do have race conditions within your code, you're screwed. I'm sorry. There's no person on the planet that can help you. But if those threads are communicating within, synchronized blocks, or at least try to reach barriers that are common to them, it should work predictably and consistently the same for the same seed, which I think is quite nice. This is my personal trademark. I came up with this. So if anybody registered that, I was first, okay? Thread leaks. You may want to detect threads that have been spawned by a test and, try to get out of your scope of a single test method. Why would you want to do that? The Lucene developers may want to address that question later on. it's interference, basically. If you leave a background thread running somewhere, then it may interfere with other threads and give you false, failures in places where, the failures are not actually happening. So the assumption is a test is really isolated, okay? It may start its own subthreads, but they all need to converge in the end and shut down. And this is both true for a single test case, but also for the suit. If you have a suit that starts threads within the before hooks or before class hooks, it's also going to work. So these background threads can actually run for the whole duration of the suit. I don't know if it's useful, but they can do it. Another thing that I've introduced is a timeout rule. So you may want, once your tests hang on the build server, it's kind of tedious to go to the build server, try to dump a Stacktrace remotely and see what's going on. So I tried to implement that so that the test framework actually takes care of stopping threads and dumping their Stacktraces. And I know Simon disagrees, but the idea is simple. You don't want any interference in the background. If there are threads that you cannot stop, you should just system exit. I mean, there's just no point of going any further. I don't know. I'd like to tell you a little bit about threads and maybe convince Simon that it's actually safe to do that, at least to a point of it's not going to bite you. Well, if you have code that does any I/O or does any monitor access or sleeping, then calling interrupt on that method, or in this case, the runner calls interrupt first on the thread. Interrupt is like a silent, quiet, graceful poke saying, hey, why wouldn't you just stop and terminate, okay? So this is graceful. And what happens is the runner will say, I'm trying to terminate this thread, and it says later, OK, I did stop it. I did interrupt it. And the exception you're getting here is the exception of the thread that was the violator of the rule. So the thread that didn't, that was spawned and didn't stop, that's the Stacktrace of that thread. It's not the Stacktrace of the framework. Again, if you have a code like this that does a while loop without any I/O, without any sleeping, interrupt doesn't do anything, because interrupt is basically a flag on a thread saying, why wouldn't you please stop? Well, it's not going to help here because the violator says, well, I'm just going to spin around. But there is a method on a thread class that is called stop. And this method comes with the long Java doc saying, do not use it. I mean, it's not safe. It's going to bite you at some point. And it's true. I mean, it's not meant to be used on an everyday basis. But in this case, what it does is, at the safe point, to be honest and to be specific, at the safe point in the generated code, in the JIT code, at the safe point level, it will throw an unchecked exception, thread death exception. So you can't predict when it's going to happen, and that's what's dangerous. But it will unlock all the monitors. It should execute all the finally clauses. And in this case, I'm sorry, it will execute all the finally clauses. Did I say it should? No, it will. It will. I'm sorry. No, it will. It will. Yes, I'm sure it will. So in this case, the thread is actually terminated at that method, and it stops with the thread death. Now this method, if you've watched the Highlander, this method cannot be killed. Once you get there, man, it just cannot be killed. So, and there is just no way, physical way to do that. So the framework will just say, I could not log, I could not interrupt or stop that thread. I'm passing on. I mean, and this is the only point where I don't know what to do. I mean, honestly, this is probably up to the decision of the community whether to stop the tests and ignore all the tests from now on, which is good because it won't pollute the stock traces or output with some random noise, or maybe system exit. I don't know. I don't know. But if you do run it in Eclipse, for instance, the Christopher Lambert will give you, a failure saying, I could not be terminated, God damn it, and I'm not asleep right now. Advanced testing. Now, this is the part where it gets tricky. I mean, in some circumstances, you may want to experiment with simulating I/O problems or network problems. And this is hard, because what you need to do is either pass mock objects that behave like they're real objects but do have that additional functionality, or I don't know, put ifs and system globals, and it just gets ugly and not nice. So the same goes for triggering like unusual interactions between objects. These are extremely difficult scenarios to test. So what I know this is not the favorite of many people, and I don't think as a programming methodology this will ever live, because it's just, it's wrong. I mean, you can't write a program in aspect-oriented programming ever. But this particular tool, as a tool, is great. I mean, it can post-process your product clusters for tests and inject the code that would otherwise clutter your real production code. And just as an example, you can do it statically or at runtime, which I make a distinction between. At runtime, you just override the system class loader, and it does the weaving while loading classes. And it's really convenient and safe. I mean, it's not going to do anything wrong. So as an example, this is a simulation of I/O issues, okay? I/O issues meaning slowing down the disk access or causing artificial I/O exceptions. This is the product code. So we have a method that reads a file, converts it to a string using a given char set, nothing fancy. This is a test on top of that product code. What it does is it creates a new temp file, writes it to disk with the random Unicode string, and then tries to read it back and compare the results. They should be identical. These are the product and the test. Now on top of that, you layer an aspect saying, what are we interested in? Well, simplifying, we're interested in all the places within the code that have a call to a constructor of a file input stream or a constructor to a random access file. This is simplification, but you get the idea. Now, to slow down disk access, we will just insert pauses at any method that is starting with read and has any subclass of, and is a subclass or called on a subclass of an input stream. So any object that is a subclass of input stream and has a method that is called read will actually be wrapped within our aspect. What we also care about is that we want this to execute only if the thread running the code is under the control flow, meaning it's under a method. And this is what was expressed here. So we're interested in threads executing under any method that is annotated with the test annotation anywhere under. So a Stacktrace, if there's a method annotated with test anywhere under, we're calling something that is opening a stream, for instance, bang, we're wrapping it with an aspect. And this is an aspect saying, before any read on a stream, if we are in a testing thread, from the context of the current, randomization runner, get the random, and within the 25% error rate, sleep somewhere between 250 milliseconds to 1,500 milliseconds. It's clean and lean, okay? And if you're not convinced, I mean, there are tools to show you that this is the place in the code where your aspect will be actually woven. It's simple. I mean, if you decompile the code, it's actually this code being copied in there. So it's what you could do manually. It's just, it's a tool. The same thing for I/O. This time we want to wrap around. So we want to wrap around any calls to constructors and randomly throw a simulated I/O exceptions. This may interest you, Uwe, because this is a method that calls on that throws an unchecked exception. I'm sorry, a checked exception and doesn't declare it. Like it. All right. And if you run it, you'll see that some of the tests are failing. Some of the tests are slowed down like we wanted to. And if you run it 3 times, you'll see that there is no pattern. It's random. I mean, really, every single execution will either fail or not. It will either slow down or not. You can switch aspects on and off depending on what you want to do. it's really convenient. Now, the same thing can be done for resource tracking, but I left it to you as an exercise. And if you send me a correct solution, I'll give you a little gift. Promise. So, runtime engineering, I know, that might have sounded a little bit esoteric, but it's not, really. Try it. It's really cool. It's very powerful. It's flexible. It does require some effort to learn how to construct point cuts, but it's simple. It's that simple. The only problem I see with that is that it's not transparent. I mean, you need to actually look at the logs of where it was woven and if the code actually was affected or not. But it's, one thing to do and many gains. Summarizing, I think randomized testing is a very promising direction. I like it very much. It helped discover many bugs, both in Lucene and our code. I'm sorry, within Carrot Search and within the Hotspot virtual machine as well, because we've reported a few bugs to Hotspot that were directly connected to execution on this paradigm. There's some tool support. If you're interested in what I've shown, there's a GitHub account where all the code connected to randomized runner is or the coding takes place. Right now it's separate from Lucene. It doesn't have anything to do with Lucene yet, but it would be really great to port it back to Lucene. The problem is it's a huge effort. So if you want to lend a hand, I'd be very grateful. And that would be it. Thank you very much.